Are we at risk of crossing a planetary tipping point? Are we at risk of irreversibly pushing the planet on a trajectory where it would unstoppably drift away from a state that can support human life as we know it? We don't have the answer yet, but I can tell you that we are forced to research this question today.
Recently in the news, we've heard about things like the North Atlantic overturning circulation, the Amazon rainforest, Arctic sea ice, for example, as systems that have, we might call them nonlinear responses, meaning that the response of the system may be initially incremental, initially slow, but at some point you give the system a big enough kick and it's no longer gradual, and the change becomes rapid.
You could actually imagine a glass of water on the table, and then at some point the table comes to an end, and global warming basically is pushing the glass of water closer to the edge of the table. For every push that you push the glass to the edge of the table, you have a little more effect. And then if you push it across the edge, then there's a nonlinear effect and the glass falls over. And the nonlinearity here is that even if you have a very small push, the effect is then very large.
It describes a point where the system moves in a completely different state without further pushing, just by internal dynamics. And so to tip this a little bit, I have to push with my feet here, but I will reach a point where I don't need to push any further, and it will by itself completely fall over.
But once you tip, you're in a new state of the system that is itself somewhat stable. So once you sort of transition from one state to the other state, beyond that tipping point, it can be difficult to come back from it. That once we cross them, even if we cool the Earth thereafter, we're stuck with the impacts for hundreds or even thousands of years.
So we're talking massive changes. You would have a rate change, the sea levels would rise faster, and it would be irreversible. That's why we're so worried about tipping points, because you pass a tipping point and it's a point of no return.
So far, we've seen somewhere between 1.3 and 1.4 degrees centigrade of global mean warming, and that doesn't sound like a lot, right? Because the difference between today and tomorrow's weather, wherever we're sitting at the moment, is probably more than 1.5 degrees centigrade. So you might ask, what's the big deal? But to put that into perspective, the difference between today and the last ice age, when there were hundreds of feet or even thousands of feet of ice overlying places where there are today major cities in the Northern Hemisphere, is just a handful of degrees centigrade. So in that context, 1, 2, 3 degrees centigrade of global mean warming, that kind of the range of warming that we've already surpassed or are on track to meet in the coming decades, is just this massive, geologically significant amount of warming, and that usually takes many thousands of years to occur when it occurs naturally, but something that we're going to see in less than a century, and literally within an individual human lifespan. So just phenomenally rapid change in the context of Earth history.
1.5 is a big number. How can it be that people in general don't understand what 1.5 degrees Celsius of global mean surface temperature rise really means? That it is a really big number. And to explain that, one has to look back at our planet's journey over time. For the past 3 million years, which is the geological epoch we call the Quaternary, which is, in my view, the only time of relevance for us, because it's only in the Quaternary that we've had a planet that resembles biologically, chemically, physically the planet that we know today, with ice sheets, with hydrological cycle, with the carbon cycle, with oceans, with the continents, that the planet that we know is the planet of the Quaternary. Our understanding today is that the temperatures on Earth during this entire 3 million year period have never exceeded 2 degrees. So the warmest global mean surface temperature, the deviation from the 14 degrees Celsius, that's what we use as a reference point. 14 degrees Celsius is the average temperature before we started burning fossil fuels. So over the past 3 million years, we've gone, stayed under 16. It's only +2. and deep ice age is -6. So I call this today the corridor of life, that everything we know, everything we cherish, everything we depend on has been evolving within this very narrow range, never exceeding 2, never going below -6. -6, deep ice age, +2, warm interglacial. During the last 3 million years, we've had 6 to 8 warm interglacials, and it's only in the last 1 million years that we enter what is called the Pleistocene, where the planets start dancing between these 100,000-year-long ice ages and shorter interglacials. And that's what is called the Milankovitch cycling, and it's all driven by our journey around the sun and the wobbling of the axis of planet Earth. So that is the 1 million years that we understand and have as a reference point. We have, as modern humans, existed on planet Earth during the 2 most recent ice ages, so only 250,000 years. So we've had 2 ice ages and 2 interglacials. One is the Eemian 100,000 years ago, and then the Holocene, the most recent 10,000-year period. So the Holocene is a warm interglacial. It is a 14 degrees Celsius planet. It's inside this corridor of life, the +2 maximum warmth to -6, but it's even more narrow. It's actually 14 degrees Celsius ±0.5. 0.5. So already today, at 1.45, we are actually almost a magnitude 3 times outside of the warmest temperature on Earth since we left the last ice age. I mean, 1.5 is a very big number. And this impacts everything on planet Earth. It changes the oceans, it changes biology, it changes temperatures, it changes heat, it changes freshwater flows. Every 1 degree Celsius of warming adds another 7% of moisture in the atmosphere. We're simply powering up the whole system with more energy, more water, more extremes, and that is what happens already at these what can be perceived as low numbers, but they're actually gigantic numbers because the corridor of life is so narrow. And why can't we talk about the last 10,000 years as being so significant? Well, it's very simple. During those 250,000 years when we've been modern humans on planet Earth, we've been just a few million people, we've been hunters and gatherers, we've lived through ice ages, we've had huge variability in terms of environmental conditions and therefore living conditions. To put it simple, we had a rough time. We lived in caves, we were nomads, we were hunters and gatherers, until we leave this last ice age and we come into this extraordinarily stable last 10,000 years. And we have just been in the Holocene for roughly 2,000 years. And what do? We domesticate animals and plants. We become farmers. We go from being hunters and gatherers, nomads, to becoming sedentary village dwellers and cultivating our food. And off we go in the innovation pathway and differentiation of technology that gives us the modern world of today. And most evidence shows that the reason we could do this is the stability on Earth during the Holocene. Spring, summer, autumn, winter comes back predictably every year. Rainy seasons come and go predictably every year. In the temperate zone in May, temperatures rise high enough to be able to plant, and then you have 3 months, and then you can harvest. And every year, that summer period has been something we can count on. That's what makes the Holocene so special. The reason why the planet has been able to stay within this extraordinarily stable state is not only that our forcing from the sun has been reasonably stable, it's also because of the feedbacks in the planet. So a healthy planet has been able to buffer different stresses from volcanic eruptions, earthquakes, and now most recently, human-induced fossil fuel burning. And a healthy planet buffers by taking up 90% of heat in the ocean from fossil fuel burning, 50% of carbon dioxide, 25% in the ocean, 25% on land. And that is a planet that applies its biogeochemical processes to try and stay in the Holocene, to try and stay within the corridor of life. And now we're pushing ourselves out of this, and we are at risk of crossing tipping points, which would then irreversibly knock ourselves out of that Holocene state.
When you speak to something like tipping points, there's 9 planetary boundaries that have been defined by scientists, and we're close to the edge of many of those planetary boundaries. And the reason why this is important is because humanity has really lived in an environment and in a climate that has been very stable for hundreds of thousands of years. That yes, we've had changes with ice ages and warm periods, but generally speaking, we've had the same types of biodiversity with some wobbles in sea level. What we're seeing now with this rapid change of climate and rapid warming of our atmosphere from greenhouse gases is the concern from scientists whether we're reaching these tipping points where things like the Greenland ice sheet, for example, may suddenly tip from being stable to being unstable. And the challenge associated with this is when we look at the models of how tipping points, how and when these tipping points may occur, there's a large envelope in those models, and there's also uncertainty in whether we've hit the bottom end of those thresholds. So when you look at tipping point thresholds, some of those we may be in the bottom end of, but because there's a range, let's say from 1 degree to 4 degrees, we've already exceeded 1 degree of global warming, but we don't yet know whether we've exceeded the tipping point for some of these things.
The Earth system, the planet, is a complex, self-regulating system where all the spheres, the hydrosphere with the hydrological cycle and the ocean, the cryosphere, all the ice sheets, the biosphere, the living part of the planet with all the biodiversity and all the plants and soils and microbes and all the species we know, but also the geosphere, the very physics of the Earth. All these spheres are tightly interconnected, and they have processes, biological, physical, chemical processes that regulates the state of the planet and the functioning of the planet. So we often mistakenly think that the way planet Earth has been oscillating from ice ages to warm interglacials, have had periods of very warm periods, as 60 million years ago when we had dinosaurs on planet Earth. These shifts between different states are not only regulated by the forcing from the sun, it's also regulated from the internal functions of these spheres on planet Earth. And what we understand from these interactions is that they are characterized by so-called interactions and feedbacks. And these interactions and feedbacks are what causes nonlinearities and tipping points.
A tipping point has 2 ingredients. One is a self-reinforcing positive feedback loop, and the other one is a critical threshold. A self-reinforcing positive feedback loop is something that amplifies an initial small change and makes it large. A good example could, for example, be if you have a microphone and a speaker next to it. You have a little noise close to the microphone, then it's amplified by the speaker, then this louder noise goes into the microphone again, and then you have this feedback loop, which you would also call feedback loop in everyday life. So this is like the core concept behind a tipping point. And the critical threshold is then the point beyond which this small change is really amplified in a self-sustained manner to a big change. So basically, you have a tipping point when you can kick off something with a small nudge and it just self-amplifies without you doing any further change, and the system just changes itself.
The Earth system, or the planet, when being in a healthy state, in a very resilient state, it has a very high degree of what we call buffering capacity. So when we burn oil, coal, and gas and emit greenhouse gases, that causes a massive energy imbalance on planet Earth. The Earth system retains more heat that comes in from the sun than it releases back to space. So this is a massive imbalance. But what happens with the planet is that the response is that the ocean takes up heat, ice sheets take up heat when they melt. 50% of all the carbon dioxide is absorbed in oceans and natural systems on land. And all these interactions is what explains when we push these systems too far, that they can flip over from the current state that buffers in a very effective way to lose that capacity. So a nonlinearity is basically when you stress a system and changes can, over very long periods of time, be linear and incremental. And that's what we've seen over the past 10,000 years, where we have humans increasingly exploiting land and fresh water, using more and more natural resources. But the planet has had this phenomenal capacity to buffer in a linear way. But it reaches a point where you suddenly see things changing non-linearly, where the rate of change accelerates. Ice melt accelerates, sea level rise accelerates, capacity for carbon uptake changes. So that's what I would call non-linearities.
In the Earth system, in a warming world, are actually not linear, meaning that each fraction of a degree of warming actually has a greater impact than the last. And I think one of the more intuitive ways to understand this that we see in everyday life is the notion of compound interest. If you have a savings account, if you have money invested in the stock market, the whole purpose, the whole hope is that you earn some particular rate of return, for that each time that money compounds, you're earning interest on a slightly larger number than you were before. So fundamentally, when we're talking about nonlinear changes, are changes that are compounding, that accelerate over time, that become larger with each increment of change. And although the warming itself that we've seen so far is in fact pretty linear, for the most part, a lot of the impacts that we're seeing have not been. And that maybe shouldn't be too surprising when we think about some of the underlying processes that are involved. We know that the water vapor holding capacity of the atmosphere increases by about 7% per degree centigrade of warming. That's pretty close to the compound interest argument. It means that every time you have an additional degree of warming or fraction of degree of warming, the degree to which the atmosphere can hold water vapor increased by a greater amount than the last time you warmed by that degree. And the challenge with this is it means that you not only raise the ceiling on how intense precipitation can become in a nonlinear sense that becomes larger and larger with each passing degree of warming, but you also increase the ability of the atmosphere to extract that moisture back out of bodies of water, back out of the land surface. So you increase both your potential precipitation extremes on the one hand and your potential flood risk, but also your potential aridity, extreme dry events on the other hand, and so potentially increase the risks of things like severe droughts. And by drying out vegetation, raise the risk of larger and more intense wildfires in many areas. That's the challenge here, is that we're sort of used to linear systems in our day-to-day lives more often than nonlinear systems. And so this is sort of requires a little bit of counterintuitive thinking.
The warmer it gets, the more extreme events you get. So for every 1/10 of a degree that increases, you get more frequent and more fierce droughts, heat waves, floods, strengthened hurricanes, more disease patterns, more fires. That is quite linear. And it's a fast variable. It happens very fast, continuously, across the world, and it hits fast. Tipping points, on the other hand, they are very different in character. They are irreversible. They can sometimes be abrupt, but many times they're actually not so fast. I mean, if the Green Ice Sheet crosses a tipping point, the rate of sea level rise will increase, and it will be unstoppable, but it's not as if the whole ice sheet suddenly just drowns us. So they cannot be compared. The tipping points are, of course, much more serious. I mean, it's the tipping points that determines whether or not we have a livable planet or not. The extreme events become very difficult for us to adapt and have massive damage, social and economic damage on the short term. Then they reinforce each other because when you cross a tipping point, you self-amplify warming, and the warming leads to even more extreme events. So there's a very strong, unfortunate, vicious relationship between tipping points and extreme events.
There is at least the possibility that we go to a point with the warming that the planet experiences overall, where some of the Earth system, critical systems, start to falter. They start to become unstable. And I think one of the greatest concerns for where we may be closest to some of those tipping points is in the biosphere, so the living part of the Earth system.
We have today mapped 16 big tipping element systems, as they're called, the big tipping point systems on Earth, that have this capacity to buffer. And they are, in a healthy state, dominated by what we call negative feedbacks, which is not very pedagogic because negative sounds not good, but it's actually scientifically the best thing we can have. A negative feedback is a system that can dampen and reduce pressure. So a healthy rainforest, like the richest biome on planet Earth on land, the Amazon basin, has a phenomenal negative feedback by absorbing carbon, and it has itself a feedback where it creates 40% of its own rainfall, which is what keeps it stable. So that is one state of this system. If you push that system too far in terms of warming and deforestation, you will cross a tipping point. You cross a threshold. And that threshold is defined by the point where the feedbacks shift from dampening to self-reinforcing. So the system loses its capacity to absorb carbon and shifts from self-generating rainfall to self-drying. And the system irreversibly tips over to become a savanna. So that is an example of a tipping point. So two criteria need to be fulfilled for a tipping element system to be defined as a tipping point system. One is that it has multiple stable states. A rainforest can tip over to become a savanna. A savanna can tip over to become a desert. It has to have these multiple stable states determined by these feedback dynamics. And secondly, of course, to become a tipping element system, they should be biogeochemically relevant for the regulation of the planetary system as a whole. Our planet is not only a complex system that has all these capacities to buffer, it's also a very powerful system. And, we have, through fossil fuel burning, added 550 and 600 billion tons of carbon into the atmosphere. So that is what has caused this whole crisis we're in. But just the soils, just the 1 meter soil layer on planet Earth contains in the order of 3 times that amount of carbon through organic matter in the soil. And if you look at carbon on standing vegetation on land, all the forests and basically all the plants that we know, it's also in the order of the same volume of carbon as the carbon that we have pumped into the atmosphere. So the planet is a very powerful system. The permafrost, just the carbon and methane in frozen soil layers in the Arctic zone contains also the same order of magnitude of carbon as the carbon that we have been pumping out over the last 200 years. That's why we have to be careful, because it means that these stocks of carbon, which are naturally there and come from geological times, they are part of this stability of the whole planet. You don't want to fiddle with that. It's one thing that we are emitting from fossil fuel burning, but you don't want the planet itself to start emitting greenhouse gases. But that's the fear.
We talk about forests as sort of an entity that is somewhat self-regulating, the tropical rainforest in particular, for example, the Amazon. The reason why that's a potential tipping point is because the Amazon rainforest, some of the rain that falls and makes it a rainforest that keeps the Amazon moist is essentially recycled. But if any part of that process, that self-reinforcing constructive feedback cycle, becomes interrupted, then the whole thing can suddenly start to fall apart. And we see this most clearly in biological systems because, of course, in the living world, things are either alive or they're not alive. They're dead. A tree in the forest is either alive or it's dead. And the reason why that's important is we sort of have this concept about living things having this very binary relationship with life and death. You're on one side of that spectrum or you aren't. But if you look at the climate system, it turns out that there are a lot of other thresholds like that. Freezing point, for example. Water is either frozen and solid or it's not. That's a very distinct difference.
One of the most important tipping point systems on planet Earth are all the ice sheets. And of course, we have the big ice sheets in the Arctic and Antarctica, but also all the inland glaciers, like the Himalayan, Tibetan glaciers. And the beauty of these big ice sheets is that they are vast white surfaces. So they reflect in the order of 90% of incoming heat from the sun back to space. So these are massive planetary scale cooling systems, and they therefore are in one stable equilibrium state. When these melt because of global warming, the surface gradually become more and more liquid, and liquid is darker than the ice surface. So you come to a point, a very specific physical point, where the feedback shifts from being dominated by this cooling capacity of reflecting heat to absorbing heat. So at a certain point, you absorb more heat than you reflect back to space. And the system becomes self-melting. And that is a tipping point. And at that point, it becomes irreversible. So that is what we're looking for in all these tipping point systems that they have multiple stable states, a stable ice sheet or a melted ice sheet, a rainforest or a savanna. And in those systems, identify the feedback dynamic which regulates the stability of the system.
One of the most prominent examples actually is the Greenland ice sheet and a feedback that is called melt elevation feedback, as opposed to another feedback, that's the albedo feedback, which is the reflectivity of the ice surface. So this decisive feedback, the melt elevation feedback, actually functions as follows. So you can imagine the Greenland ice sheet having an altitude of around 2 kilometers. So that means if you start melting down the Greenland ice sheet from the top, then for every meter or for every 100 meters that you melt it down, the surface temperature warms by about 1 degree. Just because for every 100 meters that you would climb up, you go out, you go to the Alps, for instance, climb up a hill, then for every 100 meters you climb up, temperature becomes 0.1 degree colder. And that means the other way around. If you shrink the mountain, then for every 100 meters, it becomes 1 degree warmer. And therefore, there's a nonlinear feedback once you've crossed the tipping point on top of the ice sheet and starting it to melt down and accelerating that by decreasing the height of the ice sheet.
Melting of ice consumes energy. So the fact that ice is melting actually cools the planet right as we speak in a quite devious way, because it lulls us into a comfort zone, because all our focus is on air temperature, the temperature rise in the atmosphere. Well, of all the energy imbalance that we've caused from fossil fuel burning, it's only 2% that is in the atmosphere, causing the 1.45 degrees Celsius warming so far, which we're all so concerned about, causing all the droughts and floods and heat waves and reinforced hurricanes. I mean, that is, to a very large extent, atmospheric temperature. 90% of the heat is in the ocean, but 3% is consumed when ice melts. So more energy is today used to melt ice than what we see in the atmosphere. The moment the ice is gone, that heat needs to go somewhere, and it will, of course, go in the ocean and in the atmosphere.
So we know there is a seasonality associated with the Greenland ice sheet, so it's not actually below zero all of the time, which you would expect for ice to be preserved, but there's melt in summer. There's rain falling on the top of the Greenland ice sheet, but the concern is as temperatures warm, the stability of the ice sheet will go from being stable to unstable, and then we'll have I don't want to use the word runaway effect, but ultimately we'll lose ice very quickly, and the implications of that ice loss will have a huge number of implications, including sea level rise, changing the ocean currents with that big flux of fresh water coming in, and changing the dynamics of the ocean, which then impacts people and societies that depend on the ocean for their livelihoods.
Most of these tipping points have what we call hysteresis, which means that it's easier to knock the system over its tipping point than to bring it back. So if you melt the Greenland ice sheet, it might tip over at 1.5, but to refreeze the Greenland ice sheet, you would have to go into a deep ice age before it refreezes. And we have so much evidence that we are not only coming close to tipping points, but also that we're putting pressures at the planetary level that can undermine the buffering capacity, the resilience of the whole system.
Yeah, you could imagine that as something like a domino effect, right? So, for instance, if the Greenland ice sheet starts to melt, that puts salt-free fresh water into the ocean, and the ocean currents actually function by a distinct difference between salt and non-salty water. Therefore, meaning if you have salt-free freshwater coming into the North Atlantic, that would slow down Atlantic Ocean currents such as the Gulf Stream. And by that, prohibiting that warm waters from the Gulf of Mexico is transported further north, even north of Greenland. So that actually means that there is, on the first-hand side, a direct impact through these interacting tipping elements, but also far-reaching consequences, because that means if the warm water stays in doesn't reach up to the North Atlantic, then it stays in the Gulf of Mexico, and by that can also endanger parts of the Antarctic ice sheet, and in particular the Western Arctic ice sheet, where some researchers have stated already a couple of years ago that parts of Western Antarctica might actually already have crossed the tipping point and now be on track of flowing into the ocean, in particular due to warmer ocean temperatures. So the climate system is actually interconnected and can be imagined as a system of different dominoes that interact each other.
One of these systems undergoes a nonlinear shift. It may happen that it tips one other system over and this one also starts tipping. And this can happen sequentially. So you can have a cascade. And this is also happening not in a linear way like in the typical game of dominoes, but more in a complex network of interacting parts of the Earth system. So there are also feedback loops. And it's quite a complex situation. Sometimes tipping elements, nonlinear shifts can even stabilize each other. Sometimes they can reinforce each other and further destabilize the whole system.
Everything is connected, right? The oceans are connected to the atmosphere, is connected to the land surface, is connected to the sea ice, is connected to the land ice. You can't really change one part of the system without also changing most of the other parts of the system. Remove a patch of forest in the tropics, and something in the atmosphere shifts in the Arctic and vice versa. So what you learn from doing these modeling experiments is that you can't really change one thing without changing a lot of other things. And it's often pretty counterintuitive what those responses look like in climate models, and then of course in the real world. And those folks who study paleoclimate, the climate of the past, the deep past, going back even thousands of years, we see records of this where changes were sometimes gradual, but sometimes not gradual at all. And understanding that transition from gradual incremental change to sort of these episodes of punctuated equilibrium where things change very quickly is something that I think we're still coming to terms with.
Mostly the large ice sheets, and in particular the Greenland ice sheet, could be an initiator of cascading transitions and is very decisive for interactions between between the tipping elements. And that's because the ice sheets are the tipping elements that have the lowest threshold, so the lowest tipping point. So they are the first ones to show signs of change, and by that are the initiators of possible cascading transitions, functioning by melting Greenland, putting fresh water into the ocean is slowing down, and then changing precipitation patterns over tropical ecosystems such as the Amazon rainforest. So to summarize, the large ice sheets could be the initiators of cascading transitions, and the ocean currents are then mediators between these initiators.
We're all living on this big rotating sphere that receives more energy in tropical regions than in polar regions. And so really the Earth's climate system and the weather we see is the Earth's way of redistributing energy throughout the Earth. And that redistribution of energy occurs through the atmosphere in the form of weather and storms, and it also occurs in the ocean in the form of currents.
I mainly studied the Atlantic Meridional Overturning Circulation, short AMOC. So the name itself is already a fairly good description. I'm saying Atlantic Meridional Overturning Circulation. So it's first of all, it's a system of ocean currents, of circulations. It's mainly leading to a northward transport of heat and water masses in the Atlantic. We have different current systems that, while there's a lot of mixing and turbulence, overall there's a transport from the South Atlantic, from the region around Antarctica, through the Southern Atlantic, over the equator, through the tropics, towards the subpolar North Atlantic. This is what the AMOC is, description for this transport.
AMOC itself can be visualized as a central heating system. You have a kind of warm water pipe, so to speak, near the surface, flowing north towards the northern Atlantic. There it gives off heat, like with your radiator in the house. The water cools, sinks down, and a cold blue pipe flows back out again. So it's like a central heating system.
And on the one hand side, it's a transport of water masses. And I talk about a lot of water. So the average size or basically volume strength of the AMOC is about 20 Sverdrup. Maybe a good comparison, the Amazon River, so the largest river on Earth, has a transport of about 0.2 Sverdrup. So the AMOC, about 100 times bigger. And all these water masses, as they go through the tropics, they warm up. They're pretty warm when they enter the subpolar North Atlantic, but the overlying atmosphere is, of course, much colder. So the heat is being released from the surface waters to the atmosphere, and then the water masses, because they're getting cooled down, they get denser, heavier, and there the deep water formation, or what we call deep water formation, happens. That is, water masses at the surface getting so dense and heavy that they actually sink down to deeper ocean layers. These water masses then that are down there at the deeper ocean layers form what is called North Atlantic deep water, and they actually then lead to a southward return flow of the water masses back towards the tropics. And that's what the AMOC is. It's a system, therefore overturning circulation of water masses that have a northward surface flow, warm and salty water flowing northward at the surface. There we have the deep water formation, and then we have the southward return flow of colder water masses. And with that, we also have an enormous heat transport by the AMOC within the Atlantic.
That cold blob, which is to the west of Great Britain and to the south of Iceland, is basically the region where this Atlantic overturning circulation delivers its heat and vents it up to the atmosphere. I am convinced that there has been a slowdown since the mid-20th century in that Atlantic overturning circulation. And the key symptom of that is that cold blob, because less heat is delivered there. The cold blob is just one part of a fingerprint pattern of a slowing Atlantic overturning. The other part is an excessive warming area north of Cape Hatteras along the North American Atlantic coast. And this warming area is indicative of a northward shift of the Gulf Stream. And it has been long understood already for more than 15 years that when the Atlantic overturning circulation slows down, the Gulf Stream will shift closer to the American coast.
We actually have multiple forcings that could slow the AMOC down. One hand side, we have basically external forcings, like a melting of the Greenland ice sheet that is coming from out the system, so it's not part of the AMOC intrinsic, but we also have internal mechanisms that the AMOC right now is transporting salty water to its deep water formation site, and therefore it really is internally basically keeping itself up as long as it's flowing. But this could also mean that under a slowdown, the slowdown is enhanced because less salty water is being transported to the crucial areas. And that's what we call in climate physics a positive feedback.
The northern Atlantic is quite salty, much saltier than the northern Pacific, because the AMOC brings salt there from the subtropics. If the AMOC weakens, it becomes less salty. That slows it down further. And at some point, this self-amplifying feedback, weaker AMOC, less salty, makes the AMOC even weaker. At some point, this becomes self-amplifying so much that even without any further pushing, it becomes unstable, this feedback, and will basically kill off the AMOC. So on human timescales, essentially, you won't see the AMOC recover. And that is a very different ocean circulation state. It has a lot of consequences, like really cutting off oxygen supply to the deep ocean and so on. That would be, in terms of impacts on marine life, that would be quite disastrous. If you have seen the movie The Day After Tomorrow, which has such a shutdown scenario, that movie actually does depict a scenario where the AMOC has really broken down. But the slowing down effect on Europe is actually the opposite. It doesn't make Europe cold, it makes Europe hotter. And that is because the actual cold blob is still out in the Atlantic. It doesn't reach Europe, but the jet stream tends to move around the south of that cold blob. And so that means when it gets into Europe, the airflow comes from the southwest. And so if the wind comes from southerly directions into Europe, that's warm air. But now let's think of the worst case. We pass the tipping point and the AMOC will grind to a halt then. That then would cause a massive cooling in the northern Atlantic. That cold blob would expand. It would cover Iceland, Scotland, Scandinavia, even the whole of Great Britain. And it would get very, very cold there. Studies show that just the difference between the climate with and without the AMOC in parts of Norway, that would, in the winter temperatures, would be 30 degrees Celsius in the climatological average, let alone single winters. That's something yet again, but just on average, even 30 degrees colder. So that's just how massive the impact of the AMOC is on Europe. But it does have also worldwide repercussions. One phenomenon that we have seen in the Earth's history, in paleoclimate, whenever the AMOC broke down, which has happened during the last ice age, sometimes when big ice masses diluted the North Atlantic waters by sliding into the ocean. Then, when the AMOC then broke down, the tropical rainfall belts shifted towards the south. That is also relatively simple physics. Where do we have the tropical rainfall belts today? It's where the warm air rises, because rising moist air leads to rainfall. And where does the air rise? It's where it's warmest, and it's warmest now not on the geographic equator, but some bit north of it, some few degrees in latitude. If the AMOC were to break down, they would move back towards the geographic equator. And so that means that the tropical rainfall belts will not be where they used to be. It will mean droughts in areas that are used to a lot of rain, whereas you get a lot of rain in areas which are not used to so much rain at all. So in both cases, both the ecosystems and the human structures would not be adapted then to that change in climate.
If you look at the paleoclimatic journey of planet Earth over the past, billions of years, we can talk of four specific equilibrium states of the planet. And one extreme is what we call snowball Earth. That is a planet that has gradually been cooling because of the distance of the sun. Ice sheets expand. When ice sheets expand, you get an even broader coverage of white surface, so the albedo leads to even more incoming solar radiation reflected back to space. So the planet becomes self-cooling. It's completely irrelevant for us today because we have warmed the planet so much so that there's no risk of a snowball future. Then you have the next state, which is an ice age state. That is the oscillation between interglacials and ice ages that we've seen over the past 1 million years. But an ice age is a planet which is not as extreme as a snowball, but it has two solid caps of ice in the Arctic and Antarctica, and is, as I mentioned earlier, some 5-6 degrees Celsius colder on average. And then the third state is the interglacial. That's the warm interglacial state, the one that we depend on, the one that has enabled us to develop the world as we know it. That is a planet that still has 2 ice caps. It still have inland glaciers, but it's a warm state of the planet, and it is this 14 degrees Celsius planet. And then you have the fourth one, the fourth and final state, which is what we call the hothouse Earth state. It's basically, to put it simply, a tropical planet. It's a planet that basically loses all its ice sheets, becomes such a dark planet that it absorbs more and more heat, so it gets into this self-reinforced path towards warming. It releases methane, carbon, has basically crossed so many tipping points that it reinforces warming through water vapor, methane, nitrous oxide, carbon. Very likely still has a sliver of ice in Antarctica, on East Antarctica. And the last time we had a hothouse Earth is 60 million years ago. That's where we had the dinosaurs walking on planet Earth, so well outside of the Quaternary. So these are the four. And when you look at what is at stake for us now, what are we risking today? Well, certainly not snowball. Even ice age is actually unlikely because of our fossil fuel burning caused so much heating on planet Earth that we have stopped the next ice age. So there's only one remaining risk, and that is a hothouse. We have not yet triggered that tipping point that would irreversibly push us towards a hothouse. We're still in a Holocene state. So despite the fact that we're very close to tipping points, despite the fact that it's getting really dangerous, the warming and the transgression of planetary boundaries, because we are undermining the strength of both the oceans and ecosystems on land because of deforestation and loss of biodiversity and overconsumption of fresh water and overloading of nutrients. All of this is making the planet weaker. But despite this weakness of the planet, and despite all the energy imbalance we're causing from fossil fuel burning, the consensus conclusion today is that we still have a window open to stay in a Holocene-like equilibrium state, and that we haven't, pushed ourselves towards a trajectory that would irreversibly take us to hothouse. Which is why I think it's definitely warranted to say that that is our biggest task, to avoid causing an irreversible journey where the planet starts self-reinforcing itself away from a state that can support us humans. And so far, that is not so well understood.
There are some warning signs that some of these things may not be as distant as we've assumed for some period of time, but we still can't quite put a number on it. I can't tell you today how likely it is that we see a rapid melting of the West Antarctic ice sheet that results in much faster than expected sea level rise, except to say that some of the glaciologists who study this are a little bit nervous.
We now have more and more scientific evidence that several of these are likely to cross their tipping points already at 1.5 degrees Celsius of global mean surface temperature rise. And these include the Greenland ice sheet, the West Antarctic ice sheet, abrupt thawing of permafrost in the Arctic zone, all the tropical coral reef systems, and the Barents Sea ice. So these are big systems. So we're talking massive changes. And the big question, of course, is, well, if you cross a tipping point at 1.5, what happens? You would have a nonlinearity. You would have a rate change, the sea levels would rise faster, and it would be irreversible because the dominating feedback would be self-warming instead of self-cooling. And we do not know how to return from those points. That's why we're so worried about tipping points, because you pass a tipping point and it's a point of no return.
Depending on which emission scenario we look at, so whether it's business as usual in that we draw a line on emissions that we've released over the last few years, greenhouse gases that have been released into the atmosphere, if we draw a straight line, then we're likely to hit 1.5 degrees of global warming in the early 2030s and probably 2 degrees by the 2050s. And we know from the scientific evidence, if we hit 2 degrees in the next 20 to 30 years of our lifetime, we're likely to see these tipping points occur, because then we won't be at the lower end of those ranges, but in the middle of those ranges. So there's still uncertainty, but when you're in the middle of a range, then it is more likely to have occurred than at the lower end member.
The odds that one of these things goes seriously haywire at the rapid, extreme rate of warming that we're seeing, the geologically significant rate of warming that we're seeing as a result of the accumulation of greenhouse gases in the atmosphere, the longer we do it and the more warming there is, the more likely it is that we get to one of those thresholds. It might not be West Antarctica, it might not be the Amazon. We don't know how likely it is that the North Atlantic overturning circulation might rapidly slow or even collapse at some point this century. And if it did, it would just have massive effects, especially in Europe, but really around the whole world. But we don't actually know how likely that is to happen. In fact, most scientists suspect that it's probably 90 to 95% chance that it won't happen this century. Now, the problem with that is that a lot of folks say, oh, good, 95% chance this really big bad thing won't happen. That sounds pretty good. In the context of the enormous consequences that would have for Earth society and Earth ecosystems, that 5% chance is actually not that small in context. If you were told when you were boarding an airplane that there were a 5% chance that that plane was going to crash, your response probably would not be, oh good, there's a 95% chance that it won't. You might say, there's no way I'm gonna get on this plane, right? And that would be the rational response to receiving that information as you walked in the door. At some point, once you roll the dice enough times, something is gonna come up.